All right, good afternoon everyone. And hooray, it's the weekend na. All right. Pero parang mukhang sa 175 hindi tayo masyadong makaka-relax ng konti because later tonight I'll try to upload problem set number 1. Though I don't expect you to do it on the weekend and I don't want you to do it over the weekend. Basahin nyo lang siya, right? Para magkaroon kayo ng idea at makapagplano kayo ahead. Wala naman tayong lab extra on Monday, so attendance to laboratory sessions will not be required because you're not supposed to do anything on the labs. So sayang naman yung bandwidth. So kung wala naman kayong tanong, wag na kayong pumasok sa laboratory. But if you have some questions, you need some clarifications, or gusto nyo makipag-chit chat about the problem set, then I'll be online and I'll open the meeting and see if somebody or some people will join me. Sa D2L pala to, no? Sasabihan ko rin yung lab instructors ng ibang labs that lab attendance is not required on or holding a lab class on Monday is not required, okay? So, or kung gusto niyo umattend na lang nung IMSP research webinar, that's also fine. Para medyo magaan, and then while you're watching, you can work on on some of the problems in the problem set. So initially, here's my plan for the problem set, and siguro dito na ako mag-stick. Ituloy ko yung sinabi ko last time, there would be 3 big problems or 3 numbered items, okay? Now, the first numbered item will be sort of an essay type question, so you know how I usually format those that part of the problem set. So I'll just ask you to either describe to me in layman's terms paano nag-work yung bisection method, or paano nag-work yung regular falsi method o yung secant method. Especially these methods are very graphical, or they are founded on very simple mathematical principles that I think even a layman can understand. So try to think of a nice way to write an exposition about it. Okay. And then the second part would be I'll ask you to implement a method that we haven't implemented yet in the laboratory exercises para fair, para masabi natin na lahat ng algo ay nagawa natin or na-program nyo. I think may isa tayong hindi nagawa sa lab. Alright, may ini-skip tayo na isang method sa lab. So malamang yun yung ipapagawa ko sa inyo. Isa nga lang ba yun? I think isa lang yun, no? And then the third part would be more of an objective type problem. So I'll probably make up 5 questions, which will require you to manipulate some of the formulas, some of the equations, or do some hand calculations that will involve those equations or those formulas that we discussed with the methods themselves, right? So for instance, pero disclaimer, walang guarantee na lalabas ito. Pwede ko ipa-compute sa inyo at least how many iterations is needed for the bisection method to produce an estimate that is, say, within 10 to the minus 10 of the actual root, right? So, of course, hindi nyo yan gagawin, hindi nyo yan iraran sa MATLAB gamit yung program na sinulat nyo dati, pero kailangan yung gumawa ng hand calculation. So, as math majors, you should be able to manipulate these formulas, recognize the dependence of the variables with each other, and look at the relationship of these parameters. So, hindi lang tayo yung mechanical na nagpo-prove, okay? So, kaya kailangan yung matutunan yon. The thing is, I'm going to make it an objective type problem. So, I'll put it as a quiz in Canvas. So, siguro yung iba multiple choice, yung iba true or false, yung iba you'll need to put in an answer. So, para automated na siya. And then I'll make the feedback immediate. So once you submit that quiz, papakita niyo yung explanation ko dun sa sagot. All right? My only request is that you don't share the answers to anybody, and do not post it in social media yet kasi baka meron pa kayong classmates na hindi nakakagawa. All right? So pwede siyang i-download. Pag binigay ni Canvas sa inyo yung sagot saka yung explanation ko, pwede nyo siyang i-download, i-print para meron kayong copy later, but don't post it yet. Alright? Kasi nga, for the benefit of, or para hindi maapektuhan yung iba na hindi pa nakakagawa or nakakapagpasa ng problem set. Because if I find out that the answer is already leaked, So yung mga hindi pa nagpapasa, kailangan kong baguhin yung questions for them. Baka nasimulan na nilang isolve yun on their papers, or they work on it prior. Hindi pa lang nila na-upload o natatapos yung buong item. So magkakaproblema sila. Uulitin nila yung work nila, right? What else? Okay, so I forgot to mention last time that I was also there in during the morning session of the SAF last Monday, and one key takeaway that I got there is that the industry already recognizes um, the utility of programming, and even if you're a BS Math, BS Applied Math, or BS Applied Physics graduate, parang ine-expect ng mga employers, of course, in a wide range of industries, na marunong kayo mag-program, marunong kayo mag-code, at least the basic ones, right? So kasi parang naging ano na siya, integral tool. Actually, hindi na nga lang integral, parang nagiging necessary tool na siya sa toolbox ng isang modern problem solver. And usually, we are hired to be problem solvers. Even if you say na hindi naman ako pupunta sa research or hindi ako pupunta sa academe, so malaking advantage pa rin if you learn how to code, right? So yun yung sabi nga ni Ma'am Rippy, yung from Applied Physics, that it is a very big advantage. And programming now is not for computer science major anymore. So that's one thing. So I hope that this course is giving you at least um, some familiarity with programming languages, and actually hindi programming languages kasi it's just about syntax and how you write a certain command, pero it gives you an idea of the entire programming process, okay? So yun yung gusto naming ma-develop as we go along. That's why I came on thinking na bakit kaya natanggal sa BS Math yung 174, ano? Because I think that's a very good avenue for them to practice coding. And having said that, I hope you guys try to veer away from downloading codes from, say, GitHub or from whatever sources online. Though hindi bawal, but I now think medyo wag yon yung maging go-to practice nyo week in and week out, because I think the methods, at least some of them, are very basic na kaya nyo siya talagang i-code. You just need to sit down in front of your MATLAB or your Python for 1 or 2 hours in a week para i-program yung yung code, kasi hindi naman ganoon ka komplikado yung mga formulas involved. Probably the printing, the display on the command window has a very complicated syntax, pero yung mga formulas, yung buong proseso ng program ay sana na-experience nyo. So kung straightforward yung method, try to write a program of your own, and I think that will be a good practice, or a good training for you guys. All right. So hold on, guys. Excuse me. Sorry, umatake na naman yung runny nose ko. Lagi na lang, pagka 12 to 1, ayaw yata ang pagklasihin ng 175. All right, so today we'll continue our talk about some culminating thoughts on root finding algorithms, right? So we started it last time when we talked about acceleration or accelerator methods, wherein we're complaining na yung mga methods na kinonsider natin, especially the simplistic ones, yung ano nga ba yun, regular falsy, the classical regular falsy, plus yung fixed point iterations, ang dali ng fixed point iterations. So I hope you guys can write a code for it. Level up tayo from Excel or spreadsheet, though madali rin naman siya sa spreadsheet, but it's nice to experience the coding process for it. It's not that difficult, right? Ang naging reklamo natin sa kanila, napakasimple ng implementation, napakasimple ng theoretical foundation, ay napakabagal naman ng kanilang convergence, right? So that's one thing that numerical analysts, or ano bang tawag, numerical analysts, numerical scientists, o mga applied mathematicians, pero mathematicians in general strive for, finding ways on how to improve methods. And we met one method last time, which is Aitken's delta squared process, wherein napapabilis niya yung convergence ng mga linearly convergent methods to superlinear. Okay? So, napapababa niya yung asymptotic error constant from a number less than 1 to exactly 0. So, parang kamukha siya ng Richardson extrapolation na nakita natin sa Math 174. And actually, it's very similar because we are extrapolating two previous estimates to get a new one, all right? Para makuha yung accelerated sequence of estimates to the root, okay? Now, today we'll complete our thoughts on root finding by looking at some ill-behaved root finding problems. Ito naman yung mga klase ng problems. So meron tayong methods. Alam na natin kailan nag-work itong mga methods, para saan sila design, paano sila i-implement. Now the problem is every now and then we can pass by or we can encounter a particular problem kung saan hindi nag-work optimally or hindi nag-work as expected yung mga methods natin. And bigla ka magda-doubt sa sarili mo, may mali ba dun sa code ko? Or nagkaroon ba ng bug yung code ko? Bakit ang bagal ng convergence ni Newton-Raphson when I know it's the best? It has a quadratic convergence. Bakit siya nahirapan para isolve itong problem na to? So you might think, may problem siguro sa code, may problem yata sa computer ko. But if you think about it, the underlying problem really is not on your materials, but on the problem you are trying to address. Okay? So titingnan natin kailan to nangyari, or at least some of the instances, yung mga elementary instances na nahihirapan talaga yung mga methods natin na i-solve itong mga problems na to because the problems are ill-behaved. Alright? And medyo kapag ka ill-behaved na yung problem, the fact that we are doing the calculations in a finite machine exacerbates the problem. Mas sumalaki yung problema or nadadagdagan siya. So kung ill-behaved na yung problem, tas pinagawa mo pa siya sa isang low-precision machine, like nag-compute ka using yung calculator na pangtindahan, which has a very limited memory, so ibig sabihin, kakaunting significant digits lang yung na-handle niya, then you are doomed to fail, or your method is doomed to fail. It might give you inaccurate results, or it can give you results, but it will take a long time, longer than expected. Okay. So in this chapter, we'll look at, or in this section, we're going to talk about two such causes of ill-behaved root finding problems. Una ay roots of high multiplicity. And this will really give us some headaches. All right. So, bakit nagkakaproblema tayo kapag malaki yung multiplicity ng isang root? Okay. Of course, you can avoid this. Meron tayong mga methods na hindi apektado ng pagkakaroon ng roots of multiple multiplicities or higher than one multiplicity, like Mueller's and Bairstow's method. They are less prone to inconveniences brought about by roots of high multiplicity. Okay? Pero posible pa rin sila magka-problema, lalo na yung Bairstow's, kasi yung Bairstow's ay naka-angkla sa Newton-Raphson. And we will illustrate the problem of roots of high multiplicity with Newton-Raphson. And Newton-Raphson sort of represents the best algorithm that we have for root finding kasi siya yung quadratic. So, makikita natin na magkakaproblema siya to attain that quadratic convergence kapag ka ang ating root na hinahanap ay may mataas na multiplicity. But before going there, let's refresh ourselves. Ano nga bang ibig sabihin kapag ang isang function ay may root r of multiplicity m? Now, dun sa factoring sa polynomials, alam na natin yan. Madali ang matandaan. Kapag ka halimbawa si x minus 1 cubed, alam natin si 1 ay root of multiplicity 3 kasi yung x minus 1 ay thrice naging factor nung expression na to. Alright? So, but we can extend the concept of high multiplicity even for non-polynomial functions. Alright? So, in the most general sense, we say that a root r of a function f is of multiplicity m, alright? If and only if there exists some continuous function g such that g does not vanish at r, so hindi nagzizero yung function value kay r, pero kaya natin siyang isulat na f of x equals x minus r raised to the power m times a continuous function h. Anong sabi ko dun sa sa handout? Ah, dapat ito ay G. Sorry about that. Sorry na, sinusulat ko 'to kahapon ay siguro mga 1 AM na pagkagaling sa videoke. So, yan. Nakakamiss pala mag-videoke 'no, after some time nakalabas din. Pero anyway, oversharing again. Pero yan. So, ganun din. Kapag kasi x minus r ay m times na factor ng isang function, right? And it's a product against a continuous function, then we can say that f has r as a root of multiplicity m. Okay. Now, medyo ano to eh, medyo mahirap i-operationalize itong definition na to because you're searching for a continuous function g, all right? And then mag-factor out ka sa kanya ng isang polynomial. And your function f might not be even easily expressible in terms of a polynomial times, say, a transcendental function. So, halimbawa, 1 minus cosine x or your hyperbolic function. So, mahirap pa rin gamitin si 5.11 para sa definition ng higher multiplicities, right? But if your function f is sufficiently differentiable, then an equivalent definition will be more convenient. So kung si f ay sufficiently differentiable, then we can say that r is a root of multiplicity m kapag si r ay hindi lamang root ni f, pero root din siya ng lahat ng derivatives ni f hanggang kay order n minus 1. So again, r is a root of multiplicity m if f prime, f triple prime, until the m minus 1 derivative of r vanishes or vanish. So dapat magsi-zero sila lahat, pero yung mth derivative ay hindi nagsi-zero. Okay? So ibig sabihin, pwede nyo isipin, multiplicity m siya na root, so parang dapat siya ay maging m times na root ng mga derivatives starting from the zeroth derivative, which is itself. So if f of r is equal to 0, then we know it is at least a simple root. Kapag kang f prime ay nag-zero din, then we know that r is at least a double root, or it's at least a root of multiplicity 2. If f double prime is also 0, then r is of multiplicity at least 3, and so on. Pero once nakita mo na kailan siya tumigil na mag-zero yung derivative, then alam mo na yung order na yon, yun yung multiplicity nung root. Okay? Now, some quick examples. We have the function f here, x minus 1.1 raised to the third times x minus 2.1. So here we have two roots, obviously, kasi naka-factor na siya, madaling i-deduce yung roots. First one is 1.1 because x minus 1.1 is a factor. And since it is a factor thrice, then we can say that 1.1 is of multiplicity 3. Okay. On the other hand, we can say that 2.1 is a simple root. That is, it is of multiplicity 1 because once lang na nag-appear as a factor si x minus 2.1. So you can directly apply definition 5.11 para ma-observe ano yung multiplicity ni 1.1 at saka ni 2.1. Okay? But it would be a different story if we look at g, which is 1 minus cosine x. Definition 5.11 will not be convenient in this form because how can we factor out an x minus something here, right? Kasi cosine yan. Paano ka magpa-factor ng x minus r, right? So we use definition 5.12 and look at, halimbawa si 0. I-determine ko kung anong multiplicity siya, kung anong multiplicity meron siya. Well, of course, I plug in 0. I know that is already 0 because it's going to be 1 minus cosine 0. That's 0. Tapos i-check ko ngayon, ano yung g prime? Yung first derivative ba magzi-zero rin? The answer is yes, because the first derivative is just sine, plug in 0, so you'll get 0 back. Okay. However, when we compute the second derivative, so second derivative niya, i-differentiate ko si sine, so magkakaroon ako ng cosine, plug in 0 to cosine, we'll get 1 not equal to 0. So we can say now that since the derivatives g and g prime are both 0 at 0, but g double prime is not equal to 0, then we can say that 0 is of multiplicity 2. Okay? So yun yung konsepto natin ng multiplicity. Hindi lang siya nag-apply para sa polynomials. Alright? Now, hold on for 2 seconds. Alright. So, tingnan natin yung isang specific example. Balikan natin si polynomial f. Si polynomial f ay yan. So, alam natin si 1.1 at saka si 2.1 ay of multiplicity 3 and 1 respectively. So, let's try to apply the Newton-Raphson method. Okay. Tapos, ginawa ko siya sa spreadsheet. Tingnan natin yung result. Okay. Oops. So, kaya yung landscape. Pero anyway, ito yung result. So, nirun ko si Newton-Raphson in the hopes of getting an approximate for 1.1. So, ito yung first scheme or tatawagin ko siyang first instance ng Newton-Raphson. Ang x sub 0 ko ay 0.8. And then after 41 iterations, I got to an estimate which is within 10 to the negative 12 of the actual answer. Okay? So which is expected. So nagsimula ako sa isang malapit na number doon sa root. And of course, I am expecting that the Newton-Raphson will converge. What I did not expect is the very slow convergence. All right? Kasi inabot ng 41 iterations yung run ng Newton-Raphson, even if I started at 0.8, which is just 0.3 units away from the actual root. Okay? Pero tingnan niyo yung nirun ko rito sa kabila. Yung second instance where I hope to get 2.1 as my answer. Okay? And look at this. I started at, say, sige, partida. Magsimula ka sa 70. Napakalayo nun sa 2.1. But even if that is the case, the Newton-Raphson method converged to 2.1 and it did so in a very rapid fashion. So it took only 21 iterations para yung error ay nasa 10 to the negative 10 na. I think the 22nd iteration exactly nag-zero na yung relative jump. Okay? Sorry, hindi pala to absolute error. So sinabi ko kanina, an estimate that is within 10 to the negative 10, right? But essentially, relative jump pala ito. Pero the error is very small kasi nga si Excel sabi niya na, ano na yan, halos 2.1 na yan up to machine precision. Okay? So you see the two discrepancies, both converged, but one converged faster than the other. May partida pa nga yung second instance. Kasi yung second instance, nagsimula ako sa napakalayong initial estimate. Now, let's investigate what happened, okay? Now, I did an empirical test for the asymptotic error constant, which I called AEC in this tables, right? Now, di ba yung asymptotic error constant, siya yung limit ng r minus x sub n plus 1 all over r minus x sub n raised to the power q as n approaches infinity. Tawagin natin itong lambda. Yan yung AEC, right? Tapos si Q yung rate of convergence. So tinest ko, sige nga. Dun sa second instance muna, nagawa ko na empirical test. And usually, this is how you test for the rate of convergence and asymptotic error constant if you don't have prior knowledge about it. Okay? Pero I took advantage here of the fact that I already know what R is. Alam ko ang R dito ay 2.1. So mako-compute ko yung mga quantities dito. Alright? Kasi papalitan ko lang si R ng 2.1, ng 2.1. Yung X sub n naman, nandito sila sa table. So everything is fine. And then manghuhula ako ng values ni Q. Kung siya ay linear convergence, titingnan ko, dapat yung sequence sa mga estimates sa asymptotic error constant dapat magko-converge sa isang number. Alright? So I tallied that. So Q equals 1. Kaya lang tingnan nyo siya. Mukhang magzi-zero siya. Remember, the asymptotic error constant must be greater than 0. Bakit siya nag-zero? Ibig sabihin, mas mabilis nag-zero yung numerator kesa dun sa denominator. Alright? So that means kulang yung power na 1 sa denominator para ma-offset yung bilis ng pagbabago ng numerator. That's why we know that nag-zero yung asymptotic error constant. So ibig sabihin, kulang yung Q na nilagay ko sa baba. So that means this is not just a linearly convergent sequence because the approximate AECs, all right, ay hindi nag-converge sa isang non-zero constant. All right? So, kung hindi siya linear, baka naman siya ay quadratic. But I already know this to be the case kasi nga Newton-Raphson ito, ano? So, pag Q equals 2, 2 yung ginamit kong denominator dito sa pagko-compute ng quotients na yan. Okay? Ito yung mga numbers na makukuha ko. And look at this. Right before cancellation error kicked in, nakakuha ko dito ng mga number which I think will converge to 3. Kasi nakita nyo na yung behavior from 1.39, naging 2.05, naging 2.7, naging 2.97, naging 2.995, and I don't have reason to believe that this will diverge from 3 or from a neighborhood of 2.9985. Now, I highlighted this red kasi hindi ko na kayang i-trust yung result dito. Pag kinompute ko yung ratio nung the relative errors where the denominator has an exponent 2, hindi ko na to maasahan because cancellation error kicked in. Kasi nasa ano na ba si x sub 21? Si x sub 21 ay 2.1 na up to machine precision. E ano yung actual value? 2.1. So even if this is not exactly 2.1, Excel will think, due to its limited memory, that this guy is exactly 2.1. Or this is within 2.1 beyond the machine epsilon. So pag kinompute niyo yung numerator na 2.1 minus x sub 21, alright? Eh yung x sub 21, napakalapit niyo na sa 2.1. So Excel will think that the numerator is 0, divide it by whatever previous value we got raised to the second power. Sabihin ni Excel, 0 na yan kasi nag-0 yung numerator. So yun yung ibig sabihin ko na nag-kick in yung cancellation error. Kaya hindi ko na matutrust yung answer dyan. Pero right before cancellation error kicked in, I do believe that the estimates, the asymptotic error estimates are approaching approaching a constant. In this case, it's approaching 3. Okay? And actually, this is kind of expected because alam naman natin yung Newton-Raphson, kapag siya ay nag-converge, most likely it will have quadratic convergence. Kung babalikan niyo yung Newton-Raphson method. Okay? So, yeah, this will approach 3. And actually, a quick check, na-prove natin na yung, hindi pala natin na-prove, pero alam natin na yung asymptotic error constant ng Newton-Raphson method ay approximately equals f double prime of r over 2f prime of r in absolute values. We plug in 2.1 to the to f double prime and f prime. This is actually equal to 3. So na-verify natin yung results natin ng Newton-Raphson theorem. Okay, so that means nothing is wrong. The algorithm worked fine with the search for the root 2.1 using the initial condition 70. Okay? Tingnan natin yung kabila, yung first instance. Okay? Now, gumawa rin ako ng tally. Nag-perform din ako ng empirical test in the same manner as what we did before. So, sabi ko, okay, baka naman naging linear yung convergence. Well, here I cannot trust the solutions here, okay? Kasi ito naman, dito naman yung naka-red, diyan nag-kick in na yung cancellation error. So I don't believe this values over here, okay? Pero right before nagkaroon ako ng trust issues dun sa result ni Excel, tingnan natin yung mga values. So look at this. Started at 0.69, 0.68, 0.66, 0.66, and everything here is around 0.66 and until we can observe loss of precision. So dito nga nagsisimula na siyang magkaroon ng precision issues yung computing device ko. So that led me to believe na probably this is not trustable. May word ba na trustable? I cannot trust this one. So I'm thinking, oh yeah, mukhang nagko-converge siya sa 0.66. If I will disregard the results from calculations that I think were subjected to cancellation error. Okay? So mukhang yung first instance natin ng Newton-Raphson ay nag-converge nga, pero it converged linearly with asymptotic error constant about 0.66. Okay? Or I can be more I can guess, I can have a better guess. I'll just say it's a 2 over 3. All right? Parang 0.6667. Para lang medyo fractional. So it approaches it approaches a number within the neighborhood of 0.66. So let's say it's 2/3. Okay? So mukhang 2/3 yung asymptotic error constant dito sa linearly convergent iteration ng Newton-Raphson. Okay? Tapos, bakit, sir, sabi natin yan ay quadratic dapat kasi Newton-Raphson yan? Well, I did the same empirical test. Tapos ito yung nakuha ko. Tingnan nyo, palaki ng palaki yung mga values. 75, and then naging 9,700, all the way to 5 times 10 to the 8. So it seems that these estimates will converge to positive infinity. Now, ano yung nangyayari kapag ka nakakakuha ka ng asymptotic error constant o ng hula sa asymptotic error constant that is approaching a very huge number? So that means that the denominator vanishes to zero much faster than the numerator. So parang nagiging constant siya over zero. So mabilis nag-approach ng zero yung denominator, kaya yung lambda nagiging positive infinity. Right? So paano nagiging mas mabilis yung pag-zero ng denominator kaysa dun sa numerator? Ibig sabihin masyadong mataas yung exponent na inassign natin doon sa denominator. That's why, since this is a number less than 1, a huge exponent will make the denominator go to zero faster. Okay? Kaya nagiging infinite yon pagka naggumawa kayo ng empirical test, naging infinite yung limit ng sequence, o feeling nyo magiging infinite yung limit, ibig sabihin nun, napataas yung hula nyo sa Q. So, kailangan yung babaan. So, that, at least from an evidentiary point of view, mukhang konbinsado tayo na this iteration is an underperformance of the Newton-Raphson method kasi nga hindi niya na-achieve yung quadratic convergence. The best that we can say is that probably this converged linearly with asymptotic error constant 2/3. Okay? Now, bakit nagkaganon? Sir, hindi ba to sufficient para ma-disprove yung Newton-Raphson theorem? Kasi sabi nyo dati, totoo yung theorem na quadratic yung convergence ng Newton-Raphson. Well, actually, if you take a closer look at it, hindi pala nag-hold yung Newton-Raphson theorem. So, remember, ang assumption ng Newton-Raphson theorem ay si R ay isang root ni F, pero, remember, F prime of R cannot be equal to 0. Ito yung condition sa halos lahat ng theorem natin sa Newton-Raphson. Hindi dapat mag-0 yung derivative ni F doon sa root R. But obviously, 1.1 is a root of multiplicity 3, so F prime of 1.1 will be equal to 0. So we cannot rely on the theoretical results that we had during module number 3 yata, kasi nga nag-work lang siya kapag ang derivative ay hindi naging equal kay 0. Right? So we are still lucky that the iteration converged, pero yun nga lang, linear na lang yung kanyang convergence. Now, so that's why it is a problem dealing with multiple roots. What you can do is, ano ba yung mga pwedeng solution dito? Pwede ka mag-ikens. Kasi itong iteration na to, based dun sa ating empirical test, ay nagko-converge linearly. Tapos may hula na tayo sa lambda. Ang lambda natin ay 2/3. So pwede mong gamitin si Eiken para mapabilis yung convergence nitong linearly convergent instance ng Newton-Raphson method. Tapos ang gamitin mo ng lambda n ay 2/3 for all n para makatipid ka sa computation time. Alright? Remember sa Eiken, kailangan mo yung asymptotic error constant. Alright? Tapos mag-extrapolate ka lang using 2 previous values. So you can do that, all right, para lang mapabilis ito at ma-restore. Hindi mo ma-restore yung quadratic convergence, pero at least magkakaroon ka ng superlinear convergence. Okay? Now, ano pa ba yung gusto kong sabihin dito? Okay. Now, may isa pang paraan, but this is a little bit impractical, pero this is a good theoretical exercise, all right? So, dahil ang problema rito ay ill-behave yung problem, meaning magiging suboptimal yung performance ng mga methods natin, usually for multiple roots, ang pwede nating usually gawin sa mga ganung problems ay i-reformulate ng konti yung problem. Okay? Because the issue is due to the problem itself and its very nature. Labas na yung mga methods natin. Okay? So, kung gusto mo itong i-address, kailangan mong isulat or mag-rephrase yung problem or get another problem that will give you the same expected results. Okay? Now, ang pwede mong gawin kapag meron kang multiple roots. Sorry, I'm going ahead of myself. Pero, okay. Ano nga ba yung sinasabi ko? Alright. Kailangan nating i-reformulate yung problem ng kaunti. So, kung meron kang isang root of multiplicity m, okay? Nagkakaroon ka ng yung mga derivatives na nagsi-zero hanggang sa m-1th order. Yung mga methods natin ay walang nagiging problema kapag simple lang yung root. When I say simple root, ibig sabihin ang multiplicity niya lang ay 1. So if I have a function f with root r of multiplicity, say m, pwede kong remedyohan yung problema. Hindi ko isosolve yung equation na f of x equals 0 to get r because again, it is ill-behaved kasi meron kang multiple root. Right? Ang isosolve ko na lang ay ito. Kunin ko yung m plus 1 derivative ni f, equate siya kay 0. I still know that since r is of multiplicity m, I know that this guy will be true for some value, right? May mag-exist na root. Si r yung root pa rin, yung solution pa rin ng equation na to kasi ang multiplicity ni f ay m. So nagsi-0 hanggang n-1 derivative. Pero ang kagandahan nito ay, si r ay simple root na lamang ng m plus 1 derivative ni x. And I'll call that capital F, alright? So si r ay simple root na ni f, so we don't expect any problem with solving this using, say, Newton-Raphson. Kasi nga simple root na ni big F si r. Kasi yung f prime ay ang f prime of r ay hindi na magzi-zero. Kasi ang f prime of r is little f to the m or m derivative ni little f, tapos by definition ng multiplicity m, hindi na siya magzi-zero. So it's turning a problem. We are looking for another problem or another function for which r is a root but of multiplicity 1. Okay? Pero may butas itong method na to. Una, wala tayong idea about sa root, so much more wala tayong idea kung ano yung multiplicity ng root na hinahanap natin. Alright? So kung wala tayong idea dun sa root ng multiplicity, dun sa multiplicity ng root na meron tayo, kayang i-prove, hindi ko na pinakita dito yung proof, pero kayang ma-derive sa Newton-Raphson method na kapag ka nag-converge yung Newton-Raphson method sa isang root of multiplicity m, then the asymptotic error constant would be equal to m minus 1 over m. Okay? In our case kanina, kay 1.1, multiplicity 3 siya. Alright? So, yung lambda nating nakita ay 2/3. Oops. Equate mo yun sa m minus 1 over m. Makita mo rito ay m equals 3. Alright? Which is in line with what equation 5.14 is telling us. Alright? So, kung hindi mo alam yung multiplicity, nag-run ka ng Newton-Raphson, na-observe mo yung asymptotic error constant, then mako-compute mo yung multiplicity ng root. Okay? So, alam mo na ngayon, multiplicity 3 yung root. So, kunin mo yung second derivative ni f, siya yung gamitan mo ng Newton-Raphson. And that has a larger chance of converging quadratically. Okay? Pero meron pa rin problema to. Ano pa yung problema nito? Well, sir, sige, maganda yung trick na yan, pero usually hindi natin alam yung lambda. Kasi yung lambda, ang computation nan ay actual root minus estimate over a power of the root minus the previous estimate. Okay? So if I don't know the root, then how can I find lambda? Well, dinerive natin from last time na sa Newton-Raphson, yung lambda is approximated by this sequence, yung sequence ng mga ratio ng jumps between previous estimates. Okay? So what you can do is make a table, you can compute your exabands, and then compute your lambda sub n's using this, and note saan magko-converge yung lambda sub n. Pag nag-converge yung x sub n at saka yung lambda sub n to, parehas sila nag-converge to some constants, then you can say, okay, nag-converge yung Newton-Raphson. Tapos kung ano man yung value kung saan nagko-converge si lambda n, siya yung gagamitin mo rito sa equation na to para ma-compute yung lambda. Okay? Or to get an estimate for, not ma-compute si lambda, kasi si lambda nga papalitan mo ng lambda sa n. So, mako-compute mo yung m. Magkakaroon ka ng estimate kung ano yung multiplicity ng root na hinahanap mo. But again, this is still impractical. Bakit siya impractical? Okay. Sir, para ma-compute yung lambda, para magamit ko yung approach na yan na hahanapan ko ng root yung m-1 derivative kasi sure na ako na si r ay simple root nun. Ang problema, sir, para makahanap ko yung multiplicity, kailangan kong computein ito, which is my estimates for lambdas. But the computation of this requires me to perform the entire method itself. So, ibig sabihin, nagawa ko na yung Newton-Raphson. So, bakit ko pa siya papabilisin? Alright, nakita niyo yung idea? Para mahanap lahat ng ingredients, ultimately the multiplicity of my function, of my root r here, I need to carry out the entire Newton-Raphson process, okay? Para lang mapabilis yung convergence. Bakit ko pa siya papabilisin? Nahanap ko na nga yung root eh. So why should I look for a faster method to compute it? Okay? Pero so there's no practical relevance for those things that I said. Pero yung theoretical exercise na yun, I think is nice because it revealed to us a nice interplay between the asymptotic error constant and the multiplicity of the root. Pwede ko pala itong ipagawa na ilagay dun sa problem set number 3, no? Kasi kailangan nyo lang tandaan na ito pala, pwede ako magbigay ng table ng estimates. Diba? Magbibigay ako ng sum table of this guy. Tapos tatanong ko sa inyo, ano ang multiplicity ng root na ina-approximate nitong sequence na yan? So you need to recall, oo nga pala, Newton-Raphson, pag nag-converge, ang asymptotic error constant ay m-1 over m. From observing the results from Sir's table, mukhang nagko-converge sa 2/3 yung asymptotic error constants. So ibig sabihin, m-1 over m ay equal kay 2/3. So si 1.1 ay multiplicity 3. So kahit hindi ko sa inyo ibigay yung function, pakita ko tong table na to at sabihin ko na ito ay galing sa Newton-Raphson, then you should be able to deduce that the root which this approximates is of multiplicity 3. Okay? So ganun yung mga ilalagay ko dun sa theoretical, dun sa objective part ng problem set. Okay? Now, meron pang isang tinatawag na level of uncertainty due to the evaluation of function values. Okay? So ito pa yung isang reason na nangyayari kapag malaki yung multiplicity ng isang root. So for this particular example, I lifted the discussion from Atkinson. Ang ginawa ni Atkinson, hindi ko kasi ma-reproduce yung picture ni Atkinson kasi super primitive yung calculator niyang ginamit. Pakita niyo kung bakit. Kinonsider niya yung x minus 1 cubed. Tapos obviously, here si 1 ay root ng multiplicity 3. Tapos ang ginawa niya, kasi di ba pag nagpa-plot tayo kay MATLAB or kay Desmos or sa basta isang computer software, ang ginagawa niya, ine-evaluate niya lang yung function value in a very huge number of points na pagka pinlat niyo yon, nagmumukha na siyang isang straight curve. So kung papadraw ko yan kay Desmos, ganito yung makikita natin. It's a smooth graph, but the idea behind that is ang ginawa ni Desmos, so ginawa ni MATLAB, nag-compute siya ng function value ng napakaraming points, tapos kinonect niya lang in a smooth way. So yun yung idea. Ganun ginagawa ng finite machines. Daig natin sila kasi tayo, okay, alam ko yan. Ganyan yung graph niyan. Pero sila nagko-compute ng napakaraming function values. Well, if you do the calculations for the function values of J in a very primitive machine, say a machine that has a binary floating point representation with a 9-digit rounding arithmetic. So pag ipapaplot ko si J over the interval 0.998 to 1.002. Ang gagawin ng computer na to, magko-compute siya, say, ng 800 equally spaced points over this interval, which is dense enough, okay? Tapos yun yung ipa-plot niya. Tapos pag tinanggal ko yung option dun sa plotting calculator na i-connect yung mga dots, ito yung makikita ko, yung result ng mga dots. So, kung makikita nyo, napakakapal ng band containing the function value. So, ito yung tinatawag nating interval of uncertainty. Yung function evaluation involves some unavoidable error due to the machine calculation. So, and then ang nangyayari, it might alter the root finding technique, especially if it is interval based. Kasi ito lang yung actual graph eh. Okay? Pero napakakapal niyan. So kung titingin ka rito, meron ka lang dapat isang root. Okay? Kasi dun lang magbabago yung sign, right? Everything to the left has a negative sign, everything to the right of the root has a positive sign. So parang isa lang yung root kasi once lang mag-apply si IVT. All right? Pero if you look at these little dots, and if you apply, say, the secant, the regular falsy method, or if you just apply the IVT, forget the methods first. Meron akong dot dito. Meron akong dot dito. So, ibig sabihin, IVT says, meron akong root dito. If I am relying my analysis on this discrete set of points. Ayun, may point pa ako dito. May point pa ako dito. Pag kinonect ko yan, oh, IVT na naman. Meron ako diyang isang root. So you see, na-propagate yung number of roots because of the uncertainty of the function value evaluations. So ngayon, yung search natin ay hindi lang nangyayari talaga sa isang curve. Nangyayari siya sa isang band. Kasi kailangan mo i-consider yung buong yellow region na yan. So ang kapal, supposedly, nung curve, and kasi yung uncertainty dun sa pagko-compute ng function values ay nakaka-apekto dun sa pagko-compute natin ng mga roots, especially kung meron kang interval-based method. So that's why I think those interval-based methods, or those that are relying on the intermediate value theorem, will have a hard time coping with multiple roots. Okay? And the higher the multiplicity of the function, of the root, the thicker the band will be around a neighborhood of that root. Okay? So mas kumakapal yung uncertainty due to evaluations. Okay? Now, I hope you allow me to extend 5 more minutes para matapos ko lang itong part ng module na to. 5 or 7 minutes para safe. But if you need to leave, you can go ahead. Thank you for coming today and enjoy your weekend, guys. Pero if you will stay, mabilis lang to. Yung stability naman ng roots. I did not include a theoretical analysis for this, okay? Pero I would just like to show you na meron nag-exist na mga ganitong problema. I don't know if you have seen this in AMAT 152, pero ito yung may kamukhang classical example, kasi classical tong example na to. Meron akong ganitong example dun sa work text unit 1 nung 174. Tapos I was thinking that first chapter was delegated down to AMAT 152. Pero ang idea ng stability ay kapag ka pinalitan mo yung input by a small amount, then we should, if the solution is stable, then we do not expect a very huge change in the output. So that means kung stable yung problem o stable yung situation, pag binago mo ng konti yung input, dapat konti lang din yung pagbabago sa output. However, there are some cases na pag ginalaw mo lang ng konti yung input, super laki na nung nababago sa output. Okay? So yun yung mga ill-conditioned or unstable problems. Okay? Now, this happens in nature. Maraming mga problems talagang ill-posed or ill-conditioned or unstable. And usually, we can do little about it. Okay? Kailangan mo na talagang i-modify yung problem themselves. We'll look at some of those techniques siguro when we go to linear equations. Pero gusto ko lang illustrate ano yung ibig sabihin ng unstable root finding problems. Okay? Now, this is a classic example. Ito si function f. And then obviously, looking at the factored form of f, we know that 1, 2, 3, 4, 5, 6, and 7 are all simple roots. So wala tayong in-expect na problema na katulad nung diniscuss natin kanina kasi wala naman ako ditong root of multiplicity greater than 1. Okay? Now, expand ko si f, ito yung sagot. Okay. Tapos, ano yung mangyayari kapag nag-introduce ako ng maliit na noise o maliit na error o maliit na perturbation doon kay function f? Meaning, what if I alter the function f by just a tiny bit? Okay, konting baguhin ko lang kay f, ano kaya yung mangyayari dun sa roots? Mababago ba siya ng malaki or hindi? If it's stable or if the roots are stable, then konti lang dapat yung pagbabago. Pero pag naging malaki yung impact nung maliit na pagbabago o nung perturbation o nung noise na na-introduce kay F, then tapos nag-introduce siya ng malaking pagbabago sa output, then it is unstable. Okay? Now what I'll do here is look at the x to the 6th term. It's negative 28. Now, what if I perturb it and suppose that noise affected the computation of that numerical coefficient? So instead of negative 28, gawin natin negative 28.002. Now, is this a significant change? It is not because it is 10 to the negative 5 ang relative difference. So usually pag tinitingnan nyo, minimeasure nyo kung malaki ba yung change or malaki ba yung perturbation, kukomputin nyo yung relative change. So kinuha ko yung relative change. Nag-change yung input ng 0.002 pero relative siya dun sa original value na 28. Ito yung makukuha ko. So essentially, it's order 10 to the negative 5 or more precisely, it's about 0.007%. So indeed, altering the coefficient of x to the 6 a little bit to negative 28.002 is not a big change in the function f. However, if I compute the roots of the resulting function capital F, let's call f the perturb function. Okay, siya yung na-perturb na function little f. Nag-introduce lang ako ng small change doon sa coefficient ni x to the 6. Tingnan natin ano yung roots. Well, ginamit ko na yung highest possible accuracy na kaya ng computer ko. All right. And I asked Mathematica to try to solve it symbolically. Pero irrational yung answer at hindi siya square roots lamang. So hindi na display ni Mathematica symbolically yung answer. But I asked Mathematica, sige, kainin mo lahat ng RAM na meron ng computer ko ngayon at solve mo yung mga roots na to. Ito yung binigay niya. Ito yung mga roots na binigay niya para kay capital F. And one striking observation I can make here is that look at these roots. Now from 7 real roots, now I have 2 non-real roots. Okay? Dalawa na yung non-real roots ko rito na hindi naman present before. So that's an indication that there was a significant change in the problem itself or in the solution itself. So that means this problem is ill-conditioned. Okay? Kasi unstable yung ibang mga roots. Si root na 1 ay stable kasi yung maliit na change dun sa function f just nudged a root a little bit away or nudged the root a little bit away from 1. Lumayo lang siya ng konti kay 1. It's order 10 to the minus 6 yung relative difference. So I can say na 1 is a stable root. Kasi nga, konti lang yung nabago kay 1 dun sa pagiging root ni capital F. Ganun din siguro si 2 kasi yung pangalawang root na to, malapit pa rin siya kay 2. So yung maliit na pagbabago, yung order 10 to the negative 5 na change kay little f, ay nag-cause lamang ng change of order 10 to the negative 4 dun sa root na supposedly dapat equal kay 2. So probably 2 is a stable solution. I cannot say the same for 3 and 4 kasi mukhang malaki na yung pagbabago. Kasi look at this. Nabago na 1% yung root na 3, nabago by 4.5% yung root na 4. So sige, borderline, stable, unstable yung 3 at saka yung 4. Kasi wala pa tayong measure ng ano yung stable at hindi. Usually, limiting process yon. Pero empirically, or based on this data, mukhang borderline yung 3 and 4. Okay? Ganun din yung 7. Pero the huge thing happened on the roots 5 and 6. Yung pinakamalapit kay 5 at saka kay 6 ng mga bagong roots ni capital F ay itong dalawang non-real solutions. Okay? And if I compute the relative difference from 5 and 6 respectively, I'm going to get what? This is 14%, and this is about 13% relative change. And that is big, especially knowing that the perturbation is only of order 10 to the negative 5. So yung 10 to the negative 5 na pagbabago dun sa input caused a pagbabago dun sa output of order 10 to the negative 1. So that's 4 orders of magnitude away. So that's why I can say that 5 and 6 are probably unstable roots. And the thing here is that we cannot do anything more here. Okay? Kasi nga kahit symbolically mo isolve ito, okay? Symbolically mo isolve yung roots ni capital F, malaki talaga yung agwat niya dun sa roots ni little f. So finding the roots of little f is an ill-conditioned problem. All right? And this will cause some issues, especially kasi kung nagagamit ka ng computers, tapos kinompute mo yung mga coefficients, so you might not get the exact negative 28 coefficient for x to the sixth. Your computer might give you negative 28.002. Tapos lagot ka na. Pagka nagkaroon ka ng konting loss of accuracy dun sa calculation, so magpropagate yon dun sa solution. Hindi mo makukuha si 5 at saka si 6 na roots kasi unstable sila. So that means if you have an unstable problem, it's very hard to trust the solutions from a computer. Even if it's of high precision, may chance pa rin na napakalaki nung magiging problema. Kahit supercomputer pa yung gamit mo. So I think for the problem F, we cannot do so much kasi wala tayong conditioning technique na pwedeng magamit para matanggal yung pagiging ill condition niya. But we will look at some ways on how to condition other problems to make it more stable. Yun yung titingnan natin sa next unit, which is about solving systems of equations. And I think that's where really conditioning plays a very big role. And that doon natin nakikita yung mga real-life scenarios na nakaka-apekto yung instability ng isang problem dun sa ating results. And that's 1 p.m. na, so I need to stop here. Do you guys have some questions for me? Yung exercise 2.2 about this module, i-upload ko na lang siya probably late next week kasi April 11 pa rin naman yung deadline. Okay? But I promise this will be easier than the previous exercise. Medyo may mga sabit pala dun sa previous exercise. I'll upload the answer key later today para kung di man natapos yung lab instructor nyo to grade your 2.1. Tapos gusto niyo siyang basahin before you do the problem set, so that's fine. Just one quick comment. Most of you wrote, siguro guilty rin ako nito a couple of times when I discussed. Medyo may misnomer tayo sa complex versus non-real solutions. Okay. So be careful sa problem set. I'll be strict about it. Actually, sa lab exer, naging strict na ako dito a little bit. When you say complex, pag sinabi yung complex roots, kasama dyan yung real roots. Kasi ang complex numbers ay kasama ang set of real numbers, right? So ang complex, lahat ng numbers na kaya mong isulat as a plus bi, where a and b are both real numbers. So if b is equal to 0, then we will get all our real numbers. So when you say that all the roots are complex, well, that's a given, all right? Kaya siguro nag-minus ako dun sa iba na sinabi na sa number 2 yata yun na all of the roots of this function are complex. Pero yeah, totoo yun. Pero ang problema ay ang gusto nyong sabihin talaga lahat ng roots ay non-real. Kasi baka nagsabi kayo na the graph shows that all the roots are complex, which is not apparent from the graph kasi wala kang napakitang intersection mula dun sa x-axis. So be careful when using the terms complex and non-real. Okay? So pag non-real, eto na yung mga numbers na of the form a plus bi, where b is not equal to 0. Okay? So yun, yun lang naman siguro yung malaking comment. It's a problem of semantics, but be careful. We need to be a little bit, what do you call this? Precise in our language. Okay? Other concerns? Sorry, super overtime na ulit. Okay, so with that, wait for the problem set, probably later tonight. Okay, but the deadline would be on Thursday nga ba? So you have 3 items to solve. You have 4 working days to work on it. Pwede nyo gamitin yung lab on Monday to work on it. And I think that's it. So with that, guys, I hope you enjoyed the weekend. Stay safe, and let's see each other again on either Monday or Wednesday. Bye, everyone.
Thank you po, sir.
All right.